Welcome back to quantum field theory, part 2 of the preliminary. The first lecture, the first part of the lecture was accidentally cut off, so we will continue that part. This is now the part 2 of the lecture. So the interaction Hamiltonian couples electrons to muons only through electromagnetic field, not directly. So you can see that here you have the vertex for the muons, electrons, and then this here for the muons, and they're connected with the interacting particle photon. So the connection is actually given by this one here, the mu, the gamma mu, and then the gamma, that's the photon, and this is the vertex of the two vertex, the initial and then the final. So note that the index mu exists since the proton is a vector particle with 4 components. So there are 4 possible states for each component. Then we must sum over the intermediate states. Note that the sum takes the form of a 4-vector dot product. The amplitude m will always be a Lorentz invariant scalar. This is only for 4 vectors. Now, for Hi, the interaction Hamiltonian couples the electrons to the photons. The electrons and the positron to the photons with a strength of E. That is the coupling strength. Well, of course, the coupling constant would be the 1/137 for electrodynamics, or for electromagnetic interaction. So the E there would have to be the charge of the electron, and the positron is the same as the mu1 and anti-mu1 on the other vertex. The matrix element should be proportional to E. So in this particular figure, you have an electron that is parallel to the beam, and then a positron that is anti-parallel to the beam spin. So one possible setup here of spins would be the electron and the negative mu1 being right-handed. So here, if you use the right hand, the electron and the mu1 are right-handed. The thumb is pointing in the direction of the beam, and the positron and the positive mu1 are left-handed. This means that the direction of the thumb, of your right thumb, is opposite to the direction of the beam. So in the figure, the electron and mu1 have spins parallel to their direction of motion. They are right-handed, and the antiparticles are we call left-handed. So the electron and positron spins add up to 1 unit in the momentum, in units of angular momentum in the z direction, as you can see here. So they add up to 1 here, because this is like counterclockwise, and this one is also counterclockwise. So they add up. The 1/2 here adds to 1/2 here. But if the spin is opposite, of course they add up to 0. So they add up to 1 in that case. The photon coupled to the E plus E minus should have the correct polarization to match the same angular momentum to conserve the momentum of HI. So in this case, the photon, in that case, the photon should also have the momentum 1. So this is now the polarization of the photon. So at the vertex, the momentum should be conserved. So there. So our this one here would have to be proportional to this one, this quantity. By the way, here the polarization of the photon is just on the xy plane. By the way, the z direction is the horizontal line. Yeah, the z and negative z direction there. So the photon would be polarizing on the xy plane, going up. So this is the z direction, and the photon would be polarizing up here. So that is why you only have components of x and y here. So the mu1 matrix element should have a polarization corresponding to the 1 unit of angular momentum along the direction of mu momentum k. So to obtain the vector, just rotate this with the angle theta in the xz plane. So you would have this as the polarization of mu minus. It has now a component on the z. So by the way, it is only with the angular the angle with the horizontal is with the z-axis, so you would have this form as your mu1 matrix element being proportional to. So the I retains its direction, only the x and the z change direction. So you have cosine here and the sine theta here and the cosine theta here. So you can do your research on this, and it will help you understand what happened. So to compute the amplitude m, the complex conjugate of the vector, we dot it with the star, which is this one here. So we will now have dotting this one, dotting this one and this one would be equal to this. By the way, when you get the dot product of this one here and this one, so this one would be a row, matrix, and this one would be the adjoint of of this matrix, transpose and complex conjugate. So it will give us this result. So the negative sign here is because you have a particle and antiparticle with opposite charge. So if you multiply them, that gives you negative. So if you, by the way, if you consider that the theta is 180 degrees, then the amplitude would be 0. Now, we were talking about electron being right-handed and the positron being left-handed. But how about when the positron and electron are both right-handed here? So it is more difficult to explain that one, because like we are adding angular momenta in the 4-dimensional Lorentz, so we must take into account not only spin but also the transformation properties of states under the boosts or boosted states. It will turn out that the Clebsch-Gordon coefficient couples a 4 vector to the state here of massless fermions is 0, as are the 11 other amplitude in which either the initial or final state has 0 total angular momentum. In that case, the sum of the spin of electron and positron is 0. So the remaining non-zero amplitudes can be found in the same way that we found the first one. So these are, so you have the right-handed electron, left-handed right-handed the first one is right-handed electron, left-handed right-handed electron, left-handed positron, producing a right-handed mu1 and left-handed anti-mu1. This one is a right-handed electron, left-handed positron, producing a left-handed mu1 and right-handed anti-mu1. Left-handed electron, right-handed positron. So if you have right-handed electron and right-handed positron, it gives you a 0 amplitude. Or a left-handed electron, left-handed positron gives you also a 0 amplitude. So only when the electron and the electron is right-handed and the positron is left-handed is the only combination that gives you a non-zero amplitude. So these are the 3 other remaining combinations that are non-zero. So all in all, you have so what happens here? So what happens here is that you will get the square of this one, the square of this magnitude, amplitude, and also the square of this, the square of this, the square of this. You add them all. So you add all of them, and then you will get something like -4, or I mean, you will get something like 4e to the 4 times 1 plus cosine squared theta. So you will get that amplitude square, and then you use this identity, and divide again by divide again everything by 4, because you're doing spin averaging. So you have to divide again by 4. That's why you will get the whole thing to be this. So if we integrate over the angular variables theta and phi, so we'll be getting the total this total cross section. By the way, these two agree somehow with the experiment, but there are some slight difference, because and these slight difference are accounted for the next terms in the perturbation, and the next term is actually represented by 9 Feynman diagrams here. So you have how many vertices? You have 1 2 3 4 here, 1 2 3 4 here, 1 2 3 4. This one is also 1 2 3 4 vertices, 1 2 3 4, 1 2 3 1 2 3 1 2 3 1 2 3. So you have 3 vertices, and the other one is the other next order is the 4 vertices producing the same particles. So Feynman diagrams shown in the previous figure are those that contribute to the alpha cube term in the E plus E minus to mu plus mu minus cross section. We obtained the angular distribution predicted by QED for the reaction or the interaction E plus E minus by applying the angular momentum arguments. However, we use the simplifying features of the high energy limit and the center of mass frame in a very strong way. So we will also calculate that later on using general forms. So how does one perform general QED calculation? The answer is to use the Feynman rule. Feynman rules tells us how to draw the diagrams for the process we are considering, and to associate a short algebraic factor with each piece of each diagram. By the way, so if you go to the next order, you have to apply with the alpha square, and if you want to consider the next order, you have to apply you have to multiply alpha cube, and so on. So in this case, your figure 1.5 shows the diagram for our reaction with the various assignments indicated in the expression corresponding to each vertex, internal line, and external line. So the Feynman rules for the internal photon, we write I, negative I, G mu nu over Q square, where the Q square there is the momentum of the photon, where G mu nu is the usual Minkowski metric tensor, and Q is the form momentum of the virtual photon. This corresponds to the gamma and gamma in this one here, in the heuristic expression of M, of the amplitude that we discussed earlier. So for each vertex here, you have only two vertices. You have to write a factor negative I e gamma mu. This is the Feynman rules already, corresponding to the HI. And the objects gamma mu are set of 4 by 4 matrix, constant matrix. So we will know that later on. They do the angular addition of angular momentum, coupling the state of two spin 1/2 particles to a vector particle. The external lines carry expressions for 4 momentum column spinors, U, V, or row spinors, U bar, V bar. Essentially, the momentum space wave functions of the initial and final particles, and they correspond to the E plus E minus and the mu plus mu minus. The E plus E minus is the incoming, so this is represented by mu, U and V, and the mu one is represented by this one. It's the outgoing. The indices by the way, I'm sorry for that. The U is representing the particle state, and this is the V is representing the antiparticle state. So this is representing the E plus is represented by V, and the E minus is represented by U. So that's it. So, and also another thing is that the particle incoming is represented by U, and the antiparticle incoming is represented by a V bar. So this is supposed to be this one is represented by this one. I'm sorry for that. And this one is represented by this one, and this one is represented by this one, and this one is represented by this one. So sorry for the confusion. So here is your incoming particle, an incoming antiparticle with spin S here, and the antiparticle is with spin S prime and momentum P prime. The incoming particle has spin S and momentum P, and then the outgoing particle is represented by U bar with spin R and momentum K, and the outgoing antiparticle is represented by V R prime with momentum RK prime. So if it's outgoing particle, it's with a bar. If it's outgoing antiparticle, it's without the bar. So that's it. So we can now write down an expression for M, reading everything straight off the diagram. So we have the positron, the electron, and then the vertex representing Hi, and then the photon, and then we have the muon, the anti-muon, and the vertex. So if you do that, we have then an expression equal to this. And note that we used this one before in the previous pages, so we can compare then. So there is what we call trace technology that is so powerful. It helps in simplifying this expression, because we have mu here. It can contract with this. These are matrices. The mu are matrices, so we need to use some trace technology. The easiest restriction to relax is that the muons be massless if we assume that it's massless, and if the beam energy is not so much greater than the mass of the muon. All of our predictions should depend only on the muon mass over the energy of the center of mass. The electron is actually 200 times lighter than the muon, so it can be considered massless whenever the beam energy is large enough to create muons. Using Feynman trace technology, it is extremely easy to restore the mu1 mass to our calculation. When the spin states of the initial and or final particles are known, and we still wish to retain the mu1 mass, the calculation becomes cumbersome but not difficult in principle. But all this calculation will be done later on, no? But yeah, we reserve the calculation, the formal calculation later on. So when the spin states, so the trace technology can be generalized to this case, but it is often easier to evaluate expression 1.10, which is this is 1.10. Using the explicit values of the spinner's UV. The process E plus E minus, on the other hand, to E plus E minus, known as the Baba scattering, is a little difficult because it is more tricky, and you are actually dealing with two lowest order diagrams. So this one is the first one, and this is the second one. So you have to consider two processes. Other processes contain photons in the initial and or final states. Example, the Compton scattering, for which the two lowest diagrams are shown in figure 1.7 here, and the Feynman rules for external photon lines and for internal electron lines are not complicated. Figure 1.7 showed two lowest order diagrams for Compton scattering. So they have a different form. you will deal with if you will deal with a particle as the intermediate particle, or the one that's connecting the two vertices, it has a different form. It's not anymore this one. It's different. So this chapter just introduces you how to briefly understand the role of quantum field theory in simplifying the calculation. So we will deal more with this in the next chapter. For the meantime, this is the end of this chapter, and we will start with a new chapter in the next lesson, or in the next lecture, I mean.